long before this cup is safe to touch? It's pretty hot in there. Well, today let's talk about transient heat transfer, or being able to predict the temperature of things as a function of time as they cool or heat in response to their environment. Let's get started. So let's talk today about unsteady, or in a sense time varying. Unsteady or time varying heat transfer. So this can enable us to answer questions like, at what time will the temperature of my coffee cup or my teacup get cool enough for me to handle? At what time will certain things reach a certain temperature? Or will heat flows go above or go below certain values, right? So, very rarely in real life do we have systems that are perfectly in steady state. A lot of times we might want to say, hey, when does something happen, or how long does it take for something to happen? So this is the kind of questions that that today's lecture will be able to answer, at least in the context of some of the simpler cases for heat transfer. So we're going to introduce this idea of lumped capacitance. And this is heat capacitance in the context of heat transfer, right? Not electrical capacitance like little capacitors that you would use in your circuits, but sort of a heat capacitance, which we'll kind of define in just a minute. So this idea of lumped capacitance, which kind of will be a sort of simplifying case where we sort of take our whole system and kind of lump it together and sort of consider its average temperature as that spatially average temperature varies with time. Then we'll proceed with an example problem. Where we could have microparticles dropping into a cool bath, and we might want to explore, we might want to derive what their temperature is as a function of time. So we're going to do an example problem, and this example problem is going to be broken down into many steps. As with many of the other example problems that we've done, we're going to do conservation of energy. And when we do conservation of energy, we're going to end up with a differential equation that's potentially kind of messy, but we can end up getting a solution to this differential equation in some cases if the surface temperature of our particles, we're basically going to be doing, if I have particles that sort of drop into a bath and then cool once they've entered the bath, we'll be looking essentially what the temperature of those particles is as a function of time. So if we consider, surface temperatures and core temperatures of the particles, we might say, hey, does the surface temperature, how close is the surface temperature to the average temperature of the particle? And what will enable us to answer this question is this new quantity that we're going to be talking about called the Biot number. And basically, a kind of rule of thumb on the Biot number will enable us to, maybe solve this equation or maybe not, depending on what the Biot number's value is. So if we get an acceptable Biot number and the surface temperature meets the average temperature, we're going to end up with the differential equation that relates temperature and time as well as some given constants for the problem. We're then going to solve that differential equation, and when we get that solution to that differential equation, we, spoiler alert, are going to end up with some as of yet unknown constant of integration. And the way we resolve as of yet unknown constants of integration, well, historically we've resolve them with what are called boundary conditions, where we sort of know what velocity or temperature is at various spatial points in our system. But in this case, we're looking for temperature as a function of time, so instead of calling it a boundary condition, we call it an initial condition. So we're going to apply that initial condition. Once we solve the differential equation, that's going to resolve our unknown constant, and then we're going to plot and explore the result. as well as doing some unit checks. So this is a plan, and this is a methodology that you can follow for tons, not just this particular blob cooling example, but almost any transient heat transfer type problem. So let's get started. Let's talk a little bit about what I mean by lumped capacitance. So in general, we know that if I had some blob of material, and this blob of material were initially hot, and then I took that material and plunged it into a cold bath, the surface of that material would probably cool first, and that core would probably lag a little bit behind what the surface was. But this idea, but to what degree is this surface going to differ from that core temperature right here? Well, this is where this idea of lumped capacitance comes in, right? So strictly speaking, if I were to take this, system here, this thing that's initially at some high temperature here, plunge it in a cold bath, if I wanted to really totally accurately describe, what's going on in here, I strictly speaking would need to describe temperature as a function of x, y, z, and time, right? Temperature could vary both spatially through this blob, as well as each point in this blob, its temperature would vary with time as well. So this is super complicated. Makes me a little bit sad, right? There's no way we're going to get some pen and paper solution to what this temperature profile looks like. But a lot of times, we don't necessarily care that much exactly what are the details of the temperature distribution inside the system. Under some circumstances we do, but a lot of times we don't necessarily care. We might just care, sometimes we just care about averages. And what do I mean by average? I basically mean a spatially averaged thing. So, if I sort of looked at all of the temperatures of all of the points inside this blob and averaged all of them together, that spatial average is what I might call T average. That spatial average for that whole blob could vary with time. So if I just care about, spatially averaged temperature in this system, then I might look for a simple way. Well, it's not super simple, but at least a simpler way to get T average just as a function of time, right? If I essentially average over all of the temperatures of all of these things, I've essentially ruled out the spatial dependence of all of that. If I'm just saying, hey, it's an average temperature across the whole blob, then that average temperature of that whole blob is going to vary with nothing but time. So instead of needing to derive temperature as a function of 4 messy variables, I can get average temperature just as a function of one variable, time. And a lot of time that the gist of this, average temperature is enough to make the engineering decisions that we need to analyze these sorts of systems. So that's the idea of lumped capacitance. Rather than sort of dealing with all of the details of this messy spatial variation, I'm just going to lump everything together in terms of the heat capacitance of this whole blob and just look for average temperature versus time. So that's lumped capacitance. So let's set up an example problem where, spoiler alert, we're going to use lumped capacitance to try to derive what an average temperature of some blob is as a function of time if it cools. So a lot of times, one way that you can make microparticles is you have some syringe that's that's sort of pointing down, and then you have a beaker with some fluid in it, and this is basically a cold bath. And then within this syringe, you have some hot polymer. And then you basically extrude that polymer out of the tip of your syringe, and as soon as that droplet comes off, it sort of beads up into a little sphere, or close to a sphere, and basically I can drop a whole bunch of beads into this cold bath. If the beads sink, I might say, hey, have these beads stiffened up enough by the time they sink to the bottom of the bath, or something like that. So I might be interested in saying, hey, what is the temperature of this bead as a function of time? Is it going to be cool enough to handle once other beads start piling on top of it, or once it hits the bottom of the bath, right? If I want these things to be spheres, I might say, hey, will it have stiffened up enough? Will it have cooled enough to get the right mechanical properties by the time we get there? So what types of parameters might we know about this system? Well, I might know whatever sort of initial temperature that little blob of polymer has just as it's exiting the nozzle, right? This nozzle might be heated to some prescribed temperature. So basically, I might know whatever the initial temperature what temperature this blob initially is at. I might know some information about the cold bath. I might know, for example, what the temperature of the cold bath is. Not, of course, of the water molecules immediately adjacent to the surface of one of these cooling blobs, but the temperature of the cold bath relatively far away from the surface of the blob, a sort of T infinity. If I think about this blob getting dropped into the water bath, heat is essentially convecting off of the surface of this blob and getting carried away into the fluid. And if I consider, hey, this is some convective process, if I'm going to be able to sort of predict temperature as a function of time, I'm going to also need to know what the convection coefficient is, from the surface of the blob to the surrounding fluid. So, these are parameters that I'm going to need to know about the cold bath. And then in terms of parameters of the particles, I'm going to need to know a lot about the geometry as well as the material properties of the bead as well. So some information that I'm going to need to know about the bead include its mass density, its specific heat capacity, which we talked about in a previous lecture, its surface area, its volume, and its thermal conductivity as well. Right, so basically the bead's thermal properties, specific heat and thermal conductivity, as well as its geometry in terms of its surface area and volume, and its mass density, which sort of also plays into its thermal properties as well. All of these are going to be basically important. So, yes, there's a lot of parameters that we need to know about this system, but being able to predict temperature as a function of time is going to be incredibly powerful in terms of our ability to model thermal systems. So, that's the plan. All right, so our goal is to basically derive, hey, what is the temperature of the particle as a function of time? And, if we're willing to not necessarily care about the details of, temperature at the core of the particle versus the surface of the particle versus some point in between, if all I care about is maybe what the average temperature of the particle is, I can certainly make my life a little bit easier as I proceed. All right, so this is the plan, to figure out the average temperature of this particle as a function of time, hopefully in terms of all of my known parameters as well as time. So what's the plan? Well, here we have our system. We're cooling microparticles. What's going to be our plan? We're going to apply conservation of energy to we're going to apply conservation of energy to this blob to hopefully work towards a differential equation for temperature versus time, and then we can solve it. So let's do that. So if I think about conservation of energy, I should define a control volume. Well, I'll just sort of have my particle right here, and I'm basically going to define a control volume. I'm not looking for spatially varying temperature, so shells is not going to make sense for this problem. Instead, I'm just looking to say, hey, what is the average of temperatures inside this whole system? So basically, I'm just going to lump everything inside of the blob together and define my control volume basically coincident with the solid fluid interface, with the polymer water interface at the outside. So this is the system that I'm going to apply conservation of energy to. If I apply conservation of energy, I could write down that whole messy form that we had in a previous lecture, but I sort of prefer the shorthand form of accumulation is equal to ins minus outs plus generation. So I might want to start thinking about, what are my ins and outs and all that stuff. So how is heat leaving these particles and going to the fluid? Well, it's doing so via convection, and convection right at the solid to fluid interface right here. So I basically have some Q dot convection right here, and this is defined from the solid to the fluid by definition for convection. So for our system defined just barely around the solid, that's going to be an out. So I'm going to have minus Q dot convection right here. Am I going to have any generation within the system? Well, as long as this polymer that I'm dropping out of these droplets here isn't undergoing chemical reactions as it's cooling, then I'm actually not going to have generation, right? So there's basically no reactions or electrical heaters, etc. Similarly, if my control volume basically surrounds this particle here, basically there's convection going out, there's no way for any other heat to get in. So there are basically there's no ins, there's just convection out and no other ins as well. So this is what the right-hand side looks like. Now my accumulation, to refresh your memory, this is a rate of energy accumulation. And if I think about it, for this problem, as this bead cools, it had some initial thermal energy, but as time goes on, it's losing that thermal energy to the environment via convection. So I'm going to have some non-zero rate of energy accumulation, and in particular, it's going to be, spoiler alert, it's going to be negative. So my rate of energy accumulation, I can basically say, hey, it's d energy of my system d time, right? So it's basically the rate of energy accumulation is the derivative of how much energy is in my system as a function of time. And it turns out that this is basically going to be accounted for by the convection that's leaving the system. So when I think about energy accumulation, this is something that basically has to have units of watts or joules per second. So how can I relate the energy that my system has as a function of these variables here? Well, let's hash it out. The energy that my system has, if I assume basically all of the energy in this system is essentially just thermal energy, the energy in my system is proportional to a couple of things. Well, in one way, it's proportional to basically whatever average temperature this blob is at. The thermal energy is basically proportional to temperature. So the thermal energy stored by my system is basically proportional to this average temperature here. So the thermal energy in my system is basically related to my average temperature here, but of course this has units of watts or joules per second, and this of course has units of Kelvin. So I'm going to need, the energy of my system is just joules. Its time derivative would be joules per second. So energy of my system is joules, temperature is in Kelvin. Obviously these don't match. So I need a couple of other factors here. Well, bigger blobs can store more thermal energy than smaller blobs. So what else is the energy of the system proportional to? It's not just proportional to the temperature, but it's also proportional to the volume of my blob, right? So big blobs can store a lot more thermal energy than small blobs. So that's why energy in my system is not just proportional to temperature, but also proportional to the volume. So what's that going to have? That's going to have units of meters cubed. The stored thermal energy in this blob is also proportional to the specific heat capacity, right? So if you remember, specific heat capacity was basically how many joules does it take to raise 1 kilogram of something 1 Kelvin. So the higher the specific heat capacity, the more any given gram or any given kilogram of the material, the more thermal energy it can essentially store per degree. So we have Cp right here, and that's going to have units of joules per kilogram Kelvin. All right, so I'm looking down here, you know, kelvins cancel. I'm having joules on each side, but I still have these meters cubed and kilograms. Well, what's the last thing? This specific heat is sort of a per unit mass, but my volume is sort of per meters cubed. So what else I need? I need the mass density right here to basically make both sides balance out. So that's going to have units of kilograms per meter cubed. And then we can see the kilograms cancel, the meters cubed cancel, the kelvins cancel, both sides have joules. So what can I do? I can basically take this and I can plug it into that derivative right here. Similarly, I can take Newton's law of cooling and plug it into my Q dot convection right here. So what do I end up with? I end up with d dt of T average times volume times Cp times density on the left hand side is equal to, I still have the minus sign because Q dot convection was an out, so I have a minus H times surface area times T surface minus T infinity, which T infinity is a given. All right, so this is what I have. If I basically say, hey, you know, as a function of time, the volume, the Cp, and the density are not changing. You know, there's not some appreciable like thermal expansion of these beads, you know, or like the bead's specific heat. If specific heat is a function of temperature and temperature is a function of time, you know, then I wouldn't necessarily be allowed to pull that out. But if I assume that these things are constant, then I can pull them out of this derivative here. So what am I left with? I'm left with dt average dt is equal to minus h times surface area over volume times Cp times density times T surface minus T infinity. All right, and there I have it. So what have I done? I've gotten a differential equation, but it would be nice if this differential equation were with respect to the same variable, right? So, you know, here I have a derivative, a time derivative of average temperature, but my right-hand side is in surface temperature. And this is potentially problematic, right? So, you know, there's both the average temperature and the surface temperature are hypothetically varying with time. So how might I be able to rectify this discrepancy? Well, it sure would make my life easier if things get easier if my average temperature is close enough to my surface temperature to where I can just call it, you know, some single temperature T, right? If my surface temperature and my average temperature are the same as each other, you know, or close enough to, you know, to neglect any small errors that introduces, you know, then I can just say, hey, there's just some single T that I need to worry about. The average temperature, the surface temperature, it's all the same. But, you know, sometimes this is probably going to be true, and other times it's not, right? So this is only true sometimes. So, you know, when is it true? When is it not true? You know, under what conditions does this hold? So in our problem statement, we just did conservation of energy. Now we're asking ourselves, hey, does the surface temperature equal the average temperature? And it turns out that this so-called Biot number is going to be the key to that. So let's talk a little bit about the Biot number. And to think about the Biot number, let's think about two ways that internal temperature could play out. So let's sort of divide up our page into two scenarios. Let's imagine I have one blob on one side and one blob on the other side. And let's sort of look at sort of two different kind of extremes. So when we're talking about heat transfer, within this blob and from the blob to the environment, I might want to consider relative rates of conduction within the blob to convection outside of the blob. So let's look at one extreme case here. So let's basically say conduction is slow and convection is fast. And then on the right-hand side, we'll basically do vice versa. So here we're basically going to say conduction is fast versus convection is slow. So we're sort of looking at two opposite scenarios right here. And what I might want to consider is, how is temperature going to vary? How is temperature going to vary as a function of radial position in these two cases? So, beneath each blob, I'm going to basically create these plots of temperature as a function of radial position. So if I go back to my situation right here, the polymer blob leaves the nozzle. The entire thing starts at Ti, right? The whole blob starts off at its initial temperature. So what might that look like at time equals 0? For both cases. For time equals 0, basically, internally, I'm at some initial temperature T sub I, and that whole blob is kind of uniformly at T sub I, right? So, initially I have this temperature. Initially these blobs are at this temperature T sub I, right here. Then I might consider sort of two different ways that these spatially varying temperatures could vary with time. So let's say I wait a little bit of time. I wait a little bit of time later. How might these temperatures vary, right? So if I wait some amount of time, if conduction is slow and convection is fast, the edges cool a lot, whereas the core temperature basically stays what it is. So what might that look like? The core temperature stays what it is, but the edges cool off a lot. So my edges are cooling, but my core is basically staying the same as what it is. So this is basically T greater than 0 right here. Conversely, if conduction is fast, but convection is slow, the whole sphere can basically equilibrate internally, but as heat is kind of graduated, as heat is kind of lost in the environment. So a little bit of heat jumps out, the whole sphere basically equilibrates. A little more heat drops out, the whole sphere basically re-equilibrates again. So as time goes on, for this one, instead of just the edges cooling and the core remaining intact, basically everything shifts down a little bit. So here, basically, everything shifts down. Whereas in this case, the edges shift down a lot, but the center remains kind of unaffected, right, in this profile right here. So basically, this shifts down uniformly. So this basically shifts down uniformly as conduction equilibrates temperatures internally. And you can imagine, what would look like if time went on even farther. If time went on even farther, this would just shift down some more, where basically the edges remain the same temperature, and basically uniformly temperature is dropping and dropping as time goes on, right? So these are my temperature profiles as a function of radial position here. This one, my core kind of remained a little bit unaffected, and the edges got dropped down. If time goes on, the core temperature can still drop too. It's just those edges really lose out. So, my core temperature drops a little bit. My edges drop even more. My core temperature drops yet even more. The edges are really dropping a lot. Eventually maybe I just have a little bit of heat left in here. So the question is basically, does everything equilibrate eternally and basically temperature drop mostly uniformly, except for maybe the stuff right at the edge, or do the edges really lose all of their heat, and the middle retain some heat, and then do I end up with this non-uniform temperature profile? And that question can basically be answered by, is conduction slow compared to convection, or is conduction fast compared to convection? So it turns out there's a way to essentially compare these things quantitatively, and a rule of thumb that you can use for saying, okay, how fast is fast, how fast is slow, what does it mean, for one to be faster than the other? It can, is there some number that I can calculate that will tell me it? So we can think of, conduction and convection as essentially a ratio So think of rates of conduction and convection as a ratio of two thermal resistances. And what do I mean by these two thermal resistances? Well, I might say, in a sense, there's a thermal resistance for heat, in the center to pass via conduction from the center to the outside, right? There's, I guess it's not, strictly speaking, the most rigorous thermal resistance that I could define, but, in a sense, there's this thermal resistance for heat, that heat that goes from the center to the edge, and then there's another thermal resistance as that heat that's at the edge passes via convection to the fluid at T infinity. So in a sense, there's a ratio of conduction of the thermal resistance for conduction over the thermal resistance for convection. And I'm going to put this conduction in quotes because it's not quite as sort of well formed as this nice, so when we introduced this idea of our conduction, we kind of did so for this sort of like very well prescribed geometry where we had this slab, and we had like a well-defined cross-sectional area, and we had like a well-defined thickness, this length, and there was a well-defined thermal conductivity as well, right? So we basically had these, rigorous parameters right here. In this sphere case, it's not exactly the same as a slab, but we can sort of think of this R conduction as being, something similar to some length divided by some thermal conductivity times some cross-sectional area. And similarly, when we talked about thermal resistance for convection, the thermal resistance for convection was inversely proportional to H and surface area as well. Right, so strictly speaking, this sphere doesn't really exactly have a length L, nor does it really have a well-defined cross-sectional area, because, you know, through the middle, it's a small cross-sectional area that's kind of increases as we move out radially. So there's not sort of one well-defined cross-sectional area, nor is there one well-defined length. But, you know, people sort of kind of fudge this around a little bit and say, well, you know, we can get the idea of a conductive thermal resistance and the idea of a convective thermal resistance. So what do people do? They basically define the Biot number, and different textbooks basically have, unfortunately, different definitions of the Biot number. So one definition of the Biot number that you might see is, for a sphere, is essentially h times the radius of the sphere divided by thermal conductivity. And you essentially get that by sort of plugging in R for L and R squared for AC. And, you know, it kind of fudges out a little bit, but you basically get this, you know, it kind of all cancels out to this result here. Other people instead define the Biot number as h times the volume of the sphere divided by k times the surface area of it. And in a sense, you know, you'll get a slightly different number. You get like a factor of pi and some other junk in there. But, you know, regardless of which one you use, it's really just a kind of fudge factor, rule of thumb sort of situation anyway. You know, you can use one just as long as you sort of clearly state which definition you're using. Unfortunately, you'll get slightly different numbers here, but in the context of this class, I'll basically, you know, I'll never give you a problem where your choice of one versus the other would radically change the nature of the problem. So there we have it. Okay, so take a moment now, pause and ponder. What range of Biot number should imply that Ts or T surface is approximately the same as T average? What range of Biot number basically allows us to draw this conclusion? All right, well, hopefully you've had a chance to pause and ponder. The answer is a small Biot number. So what would a small Biot number imply? A small Biot number would imply that conduction has a small resistance compared to convection. And if conduction has a small resistance compared to convection, that's basically saying conduction is fast and convection is slow. So a small Biot number basically is saying, hey, thermal conductivity is really high. And if thermal conductivity is really high, then the Biot number is small. Or my convection coefficient is really slow. And what does that mean? That means basically like heat is leaving the sphere very, very slowly, but temperatures can equilibrate very quickly. And that basically means, hey, I have basically, you know, for all intents and purposes, a uniform temperature inside of the sphere because of this rapid equilibration compared to the slow convection leaving, right? So a small Biot number sort of implies rapid temperature equilibration internally. And this small Biot number is basically what we have over here on the right. So a small Biot number means temperature is going to vary in time this way, where it sort of temperature sinks uniformly as the sphere cools. So a small Biot number basically says, hey, temperature is basically uniform, which means our surface temperature is essentially the same as our average temperature, and we're not going to have this case where we have appreciable spatial variation in temperature. So what does that mean? Well, we can go back to this differential equation here. It's easier if T average is equal to T surface, where we could just say, hey, there's just some single T that we care about, and it's only true sometimes, and in particular, it's only true when Biot number is small, and a good rule of thumb is when Biot number is less than 0.1. So I know it's not going to be exactly, you know, there might be some cases where this Biot number is, you know, and this one isn't, or vice versa. But, you know, again, it's just sort of a rule of thumb anyway. Just kind of follow this result here. So, and if you're really close to 0.1, you should kind of be a little bit uncertain about, you know, and kind of questioning of your results anyway, depending on how much accuracy is needed for your application. So here we have it. Okay, so we can basically say, hey, you know, T average and T surface, they're basically the same if we have a small Biot number. Let's see what progress we can make with this differential equation. So kind of copying our result from before, but putting it just in terms of a single t, we basically have dt is equal to minus h times surface area over volume times Cp times density. And this is equal to t minus t infinity. So here I have a differential equation on my hands. It's a first order linear differential equation, and we can solve it via separation of variables. Woohoo! Our favorite trick in the book. So what are we going to do? Well, we can bring the t minus t infinity over to this side, and we can bring the dt over to this side. So what's that going to look like? We have dt over t minus t infinity is equal to minus h times as over v cp rho times dt. So this is my differential equation. I can integrate both sides, and I'm just going to leave it as indefinite integrals for now. Remember, taking a step back, remember these are ordinary derivatives because I'm basically saying, hey, there's just some single t average right here. So t average isn't going to vary with any other variable except time, since it's already sort of averaged over the spatial stuff. You can't have this spatially averaged thing, you know, depend on really any other variables except time. Okay, so if I integrate t minus t infinity, if I sort of ignore the t infinity for now, it's kind of like integrating 1 over t, and integrating 1 over t would give me natural log of t. We could, strictly speaking, we would want to do a u substitution right here, but you could just take my word for it that we get natural log of t minus t infinity right here. And then on the right hand side, you know, this is all just a whole bunch of constants, dt. So what do I end up with? I end up with h times as over v times cp times rho times t. So I integrate a bunch of constants with respect to time. I get those constants times time. But these were indefinite integrals with ordinary derivatives. So when I integrate indefinite integrals with ordinary derivatives, then I get some constant of integration. Great. So I could try to apply my initial condition right here to try to resolve this constant. I'm actually going to do a little bit of algebra before trying to resolve this as of yet unknown constant. So if I want to try to unbury t, I can exponentiate both sides. So then I get t minus t infinity is equal to e to the minus h times surface area over volume times Cp times rho times time. And I have a plus. This is all in the exponent plus const in the exponent. If I have a sum of things in the exponent, that's equivalent to multiplying e to each of those two things by each other. So it's basically equivalent to e to the minus h times as over volume times Cp times rho times time. And then this whole thing times e to the constant. Well, you know, constant was just some arbitrary constant, right? So some constant is an arbitrary constant. E to an arbitrary constant is also an arbitrary constant, right? It's basically like it's an arbitrary constant no matter how you slice it, right? So what does that mean? Whether it's a constant or e to an arbitrary constant, I can just call this whole thing. I'm just going to call this whole thing c. So instead of my constant of integration being c, I'm just going to call e to this arbitrary constant of integration. I'm going to call that c, which I'm going to try to resolve with initial conditions. So what does this look like? I basically have t minus t infinity is equal to some as of yet unknown constant c out front times e to the minus HAS over volume times Cp times rho times time. So I can resolve this with initial condition. And if I go back to my problem statement, I know that basically once these blobs left the nozzle, they left the nozzle at some initial temperature here, and that is basically what the temperature of the blob was at time equals 0, the first sort of instant it hit the water. So my initial condition is at time equals 0, then t is going to be equal to my known initial temperature, which I'm calling t sub I. So I can sub that in. I can basically say t sub I minus t infinity is equal to c times e to the, and I can basically plug in 0 here. Well, e to the 0 is 1. Anything to the 0 is basically 1 except for 0 to the 0. So what does this mean? This basically means c is equal to ti minus t infinity. So what does that look like? I can basically do a little rearranging, and I can say t minus t infinity is equal to ti minus t infinity, or sorry, t minus t infinity over ti minus t infinity is equal to e to the minus h times as over volume times Cp times rho times time, or I could basically say t is equal to ti minus t infinity times e to the, I'm getting sick of writing this, h times as over volume times Cp times rho times time plus t infinity. And this is the final result, right? So, woohoo, mission accomplished. We've gotten to our goal of determining our average blob temperature as a function of time. So this might basically allow us to say, hey, by the time the blob leaves the nozzle and hits the bottom, if I can predict this temperature as a function of time, that might tell me, hey, have my blobs solidified enough? So we can now basically plug in any time we want and be able to predict what the temperature of that, what the average temperature of that blob is going to be. Awesome. So what did we do? We got some differential equation. Once we made our our assumption of average temperature equaling surface temperature from this Biot number, we solved our differential equation. We applied an initial condition. So now it's time to basically plot and explore the results. Hey, do our results make sense? So let's create some plots of temperature as a function of time. Let's just say that, in this case, my initial temperature is up here, my T infinity is down here. So pause and ponder as to at time equals 0. Well, we already knew that at time equals 0, my temperature is going to be equal to Ti. As time goes to infinity, I get e to the minus infinity, which basically makes this whole first term go away, when the whole first term goes away, as time goes to infinity, t approaches t infinity right here, and it's going to do so with a sort of exponential decay looking like function. So what does that mean? Basically, I start off at t sub I, and I'm going to approach t infinity with something that looks like exponential decay. So that's basically the shape of this curve right here. So take a moment now, pause and ponder. What would it look like if I increased h? What would it look like if I increased h? How would this curve change? Well, if I increased h, I'm basically increasing this term that is multiplying time. So increasing h essentially does something that appears to sort of accelerate time. So if I increased h, let's sort of put this in the red curve right here. If I increased h, then that does something that basically makes the temperature decay faster, right? And that's that makes sense too, right? If I take these beads and vigorously stir the water to increase convection, then I'm going to cool the beads a lot faster, right? Duh. If I make my convection faster, then I'm going to make the temperature of those beads drop. Of course, this is with the caveat that our Biot number is still valid, even though we increased h. But I'm kind of brushing that under the rug right now. So if I increased h, then I basically move from what looks like the blue curve towards what looks like the red curve. So if I increase h, that's doing that. Or equivalently, I could sort of also increase my surface area. Increasing h or increasing the surface area essentially does the same thing. Or decreasing the volume of my beads, right? If I have a bunch of small beads getting dropped into that fluid, the small things tend to cool down a lot more quickly than big things, right? So when I have food that I want to give to my toddler, and that food is too hot, she's going to burn herself if she tries to eat it, I cut up that food into little tiny bits so it cools a lot faster, essentially increasing the effective surface area or sort of decreasing the volume of each individual food particle. So when I want my food to cool quickly, I could blow on it to increase h, or I could cut it up to increase its surface area or decrease the volume for each individual particle. Or equivalently, if I decreased Cp or decreased the density, that would have the same thing, right? So basically, if my particles are less good at holding on heat or less massive, then they cool down quickly, right? So, you might have heard people talk about, if you've ever noticed, you might have like toast. Your toast cools down very quickly, whereas a baked potato takes a long time to cool down, and that's basically because a baked potato has a lot higher density than toast. So going from toast to a baked potato, basically your baked potato would be this blue curve right here, and your toast would be your red curve like here, cooling down much more quickly. One last thought, or question rather, before we move on. So pause and ponder. Is this valid? Is our analysis valid if t sub I is less than t infinity? So, is this analysis that we got, is this result that we got, does this all still work even if ti is less than t infinity? Pause and ponder. Well, it turns out that the result is yes, it is valid. And what would it look like? It would basically, I have my ti down here, and it would sort of exponentially approach t infinity just from the bottom instead of from the top. And so I would get basically an exponential, not exponential growth. It's still exponential decay, but it's exponential decay sort of from below rather than from the top. And in a sense, it's basically sort of a temperature difference is exponentially decaying, regardless if that temperature difference was positive or temperature difference is negative, right? So it's basically it's delta T decays. Delta T decays regardless if positive or negative initially. So that's the key takeaway. So this phenomenon, this derivation that we described here, describes things cooling just as well as it describes things heating. So hopefully you enjoyed and learned something from this lecture on transient or unsteady heat transfer, and in particular this lumped capacitance approximation that works pretty well if your Biot number is sufficiently small. So good luck with your studies of fluid mechanics. Take care. Or sorry, studies of heat transfer. Take care.